wonderful day and a warm welcome to our second live session of the MOOC at TU9. And especially welcome to our new members of the audience. Good to have you here. First of all, some short information for our new members about TU9. TU9 is an alliance of leading institutes of technology in Germany. MOOC at TU9 is a joint project of the TU9 universities all over Germany. In our overall 9-week course, we want to provide an overlook and deeper insights into key issues and contents of modern engineering. Therefore, you have now the choice to get this overlook. The course is interactive and you have different kinds of opportunities to join us. For everything, you need to log in. You need a username and a password to do so. After every portrait of one of our TU9 universities and interview to our professor, you can ask directly questions to him I'm talking to. So ladies and gentlemen, welcome to the MOOC at TU9. What are we going to do in the next 90 minutes? In our second live session, I want to give you deeper insights into models in civil engineering from cardiology to fishery at the TU9 universities in Dresden and in Munich. Today, we start with the TU Dresden and with Professor Daniel Balzani. His topic for today, modeling of fiber-reinforced membrane materials. To begin, I want to show you a portrait film of him and the TU Dresden.
Hello, my name is Daniel Balzani. I'm professor for mechanics at the Institute of Mechanics and Shell Structures, which is situated in the Department of Civil Engineering at the Technical University of Dresden. My main research topics are biomechanics and modeling of microheterogeneous materials. Part of my research is to develop methods for the numerical simulation of membrane structures, such as the new roof of the main station in Dresden. Main advantages of these constructions are that they are translucent, dirt resistant and light, enabling a slim appearance with architecturally interesting shape. These membranes are typically composed of reinforcing fibers embedded in an isotopic matrix. This is particularly interesting to my research because this is a strong parallel to soft biological tissues. The simulation of these membrane materials requires new and more accurate modeling approaches that take into account the microheterogeneous nature of these materials. In our Faculty of Civil Engineering, of particular interest is the investigation of fiber-reinforced materials on the basis of concrete in order to develop new materials that have advantageous properties. It is important for me to not only teach a high level of fundamental and advanced mechanics, but also topics that are related to research. In particular in biomechanics, students already learn how to work interdisciplinary, and this will be advantages in their later jobs.
And now I'm looking to him in person, or to talking to him in person. Welcome to Dresden, welcome to Professor Balzani, to our second live session at the MOOC at TU9. How are you today?
Yes, hello Mirko, very good to be here. Hello also everybody, welcome to the session of today. I'm fine, hope you're too.
Thank you very much, I am. In the video you showed us already, the roof of the main station, and as you said, in Dresden is one example of the development of methods for the numerical simulation of microheterogeneous materials as one part of your research. Can you give us more insights? What other relevance has that topic in our everyday life, in our world today?
Yes, basically there's plenty of microheterogeneous materials, in particular modern materials, and fiber-reinforced materials are one material of this kind, I would say. The example that we've seen in the intro was basically for roof constructions, as you said, some sort of textile membrane material, but there's plenty others. So for example, fiber-reinforced materials that are used for automotive and airplane industry, there typically carbon fibers are used. Another class of materials are, for example, multi-phase steels, which also exploit microheterogeneities to get a more advantageous behavior at the macro scale. And this enables, for example, engineering constructions that are thinner, characterized by a higher stability and lower weight. So this may also play an important role with respect to electric mobility, for example. Interesting for me in this context, of course, is that research at different scales is necessary. So in order to describe or simulate those materials, new modeling approaches are needed, and that's basically what I'm working on.
And what do you think, what future importance do you see in your research field?
Well, I expect a lot of materials that are going to be developed that in particular exploit these microheterogeneities to basically construct a new macroscopic material behavior. In this context, in particular, special couplings may be important in the context of multifunctional material, if you want. So, for example, to get a specific magnetomechanical coupling that, for example, the individual components at the microscale would not have by themselves, but as a result of their interaction, you get this advantageous macroscopic behavior. Also, in the context of biomechanics, the incorporation of microstructure information plays an important role, because there we have the special problem of doing experiments, basically. I mean, experiments can be performed, but it's rather hard to do those. And on the basis of simulations, you can get an insight into the material. So basically, the more we know from the microstructure, the less experimental data we need.
As you said, you also work on biomechanics. Why is it so important for our society?
Well, from my point of view, or let's maybe first focus on what I'm dealing with. I'm focusing on soft biological tissues, their modeling and their simulation, and in particular with respect to arterial walls, particularly diseased arteries, so for example atherosclerotic arteries. And with respect to this, I would point out two main points that may be important. The first one is that we of course want to get a higher or deeper insight into the analysis of biomechanics that take place in these tissues. As I said, simulations enable a look into the tissue, which normally by just performing experiments is difficult. And the second important point from my point of view is, of course, the optimization of medical methods of treatment. So, for example, in the case of atherosclerotic arteries, to optimize the so-called balloon angioplasty, which is typically performed then.
And why, just more detailed about our society, why is it important for me?
Well, hopefully not for you, because you may not be diseased, but of course, lots of people have problems with their cardiovascular system. Basically, severe consequences thereof are, I think, number one still of primary cause of death in the industry nations. So there's a large demand, I would say, to improve everything which is associated to treatment there.
Okay, thank you. So what do you think if we switch to the student life? What are the possibilities in the job market after finishing studying advanced computational and civil engineering structural studies at the TU Dresden?
Well, basically, the program you just mentioned, the Access program, that's a short form for it, is a 2-year master program which focuses on basically fundamental knowledge in computational mechanics and, of course, advanced classes in the context of computation simulation, computational material science, and things like that. So obviously, students that finish this program will typically find a job in research-related, for example, R&D departments of industrial companies, or research facilities, or universities, non-university research facilities, as for example Fraunhofer, Max Planck, Leibniz. That's one big part of it, I would say, and there's plenty of other options in classical engineering offices where computational simulation plays a big role, I would say.
And if we have a look deeper in your curriculum, what is the focus in the curriculum of your curriculum, basically?
Okay, you mean in the Access program? I mean, that's one of the things that we offer in our Faculty of Civil Engineering. Basically, it's some sort of computational mechanics studying with a focus on civil engineering problems. So that's the particular thing there. We offer another program, which is also a 2-year program for extended studies. The main difference is that there you can specialize in 4 different topics. It's structural engineering, environmental engineering, construction management, and also computational mechanics. The main difference here is that the language will be German. So that may be particularly interesting for students coming from abroad that are planning to stay in Germany, for example, after their studies, because from my point of view, still in industrial employers, it's quite important to speak German then. So that's maybe an interesting alternative.
Yeah, are there any German courses in the curriculum in itself?
That depends. So if we're talking about this, what I just mentioned last, then everything will be in German. In the Access program, basically everything is in English. So that's better for those students, of course, that not really have already the plan to stay in Germany, I would say.
Okay, I think we have some international members in our audience, and therefore just in between, if you have any questions to Professor Balzani, you can ask or you can write them in the chat, and I can ask him after the interview. And therefore, I have my new question or my next question: are there any students from abroad yet?
Yes, also that depends very much on the program the students are in. The students in the Access program, I would say the fraction is very large. So typically a lot of students from foreign countries come there. In general at TU Dresden, I would not say that the fraction is huge, but from my point of view it's going to change. I mean, there's, for example, this Dresden concept that we have here. That's a special institution which fosters collaboration of university with all the, with the huge amount of non-university research facilities that are gathered around in Dresden, particularly in the context of material science and biotechnology. Then there's this Welcome Center from TU Dresden, which offers direct collaboration with the immigration offices, so that facilitates a lot all the special issues that typically foreign students would have when they start. So, as you can see, a lot of things are going on right now, also due to the success in the Excellence Initiative, of course.
And what do you expect for the future?
Well, I would expect that there will be a change. So, obviously, the fraction of students from foreign countries will increase. That's my guess.
Okay, I've the first question in the chat, and therefore, what kind of analysis or optimization softwares does you, Professor Balzani, use?
Okay, I personally, of course, now the question is with respect to research or with respect to teaching. Of course, that is different. In our research, we typically use FEAP, that would be the Finite Element Analysis Program. It's developed in Berkeley in a group of Bob Taylor. And for general optimization purposes, so if you want to, for example, adjust parameters to experimental data, or in the context of uncertainty quantification, there we use the Mystique framework.
And the second part of the question is quantum mechanics really necessary for TU Dresden Advanced Computational and Civil Engineering Structural Studies course? Did you get it?
Not really. The second part, I couldn't hear it, sorry.
Is quantum mechanics really necessary for the TU Dresden Advanced Computational and Civil Engineering, so the Access course? Is quantum mechanics really necessary for it?
I'm not absolutely sure if I got the question correct. Okay, I cannot ask. So I would say, if you mean that, if you need already knowledge before studying, then I would say no, it's not necessary. It's not something you need to know before studying. And basically, I'm not really sure if a course is offered within this program regarding quantum. Sorry, what was it again? Quantum mechanics or quasi-continuum?
I think the question comes again up. Which competences, what kind of knowledge and what skills are mediated by studying civil engineering at TU Dresden? I think that's the same part of the question, just in a different way. So what skills, what knowledge is needed to study Access?
Well, basically, I would say you probably should have a bachelor's degree in some sort of engineering-related topic. Mathematics would maybe also be fine for computational mechanics, but of course engineering would be the best thing that you should already have studied.
Okay, thank you. And then another question is, how many students are enrolled every year?
Oh, that's difficult to say. It changes a little bit. In the access program, I guess that's the what the question is related to. It's like 50 approximately.
And second and third part of the question is about the structural part. Are there big learning groups or small learning groups? And do you study alone, or are you encouraged to study in groups?
I would say you are strongly encouraged, of course, to learn in groups. But that depends really on the class, I would say. There are classes where you really have a focus on, for example, implementing subroutines in an existing code or something like that. There, of course, you need to work alone on the computer, but you're in a rather small group, so you can even, during doing so, interact with the others. Then there are other classes where you have group exercises. It really depends on the class. It's difficult to say. There's not only one thing that we follow, I would say.
Okay, then a question of myself. How practical is the study program? Are there any cooperations between your institute and firms, non-university facilities?
So basically, I mean, as I said, this is some sort of program for computational mechanics with application to civil engineering problems, I would say. So there's always also an applied part of it, I would say. But of course, it's a master program at TU Dresden, a university. So a lot of courses therein are research related. So really at the edge of what we know right now or what we can do. There are collaborations. In my case, I'm collaborating with ThyssenKrupp Steel and Max Planck Institute for Iron Research with respect to the multi-phase steel projects, and Toyota, for example, to work on numerical approximation schemes. But as I said, I mean, there are so many non-university research facilities around Dresden, in particular in the material science and biotechnology framework, that I'm really looking forward to a lot of more collaborations there. I should say that I just started in Dresden, so that's maybe also a reason why there are not so many collaborations already with all these institutions.
So therefore, you think that the chances for graduates are very high, or are there more challenges to find a job? Sorry.
No, I would say that the chances to find a job are extraordinarily good from my point of view. So far, I didn't hear from anybody that didn't find a job within reasonable time. So I would say the chances are really even great, I would say.
Okay, and another question from the audience. Which future topics and challenges do you see in your research field?
Okay, in my research field, in particular in the biomechanics framework, what we are working on right now is to incorporate more phenomena, not just describing the mechanical behavior, although that's already challenging enough, but further phenomena, for example, growth, remodeling, adaptation processes that happen in the living tissue. Then we are working on the incorporation of diffusion processes, such that the effect of medicine or medical substances can be studied due to numerical simulations.
And the last question from the audience, do students need to have good programming skills, and are the programming skills taught at the TU Dresden?
Okay, basically it's already a master course, so you should already kind of know how to program. We don't require you to know every or sophisticated programming languages, but some basic knowledge should be there. Otherwise, it may be probably a little bit difficult. But really, as I said, I mean, normally the classes will focus on simple programming languages, not a sophisticated object-oriented programming skills.
So you need the language C to do so?
C or Fortran. I mean, we work in our group with Fortran. It's still an efficient programming language for doing numerical calculations. Right. So C and Fortran, that would be fine.
Okay, before we come to the task of the week, last question for myself. If you study at the TU9, what do you think is a German engineer part of, or a special effect, a special skill of engineer who studied at TU9? What do you think? What is special?
Okay, I would expect that we do not only teach the subjects themselves, I would say we also foster creativity, independence, sustainability, and also basically personalities, I would say. So it's not only learning about computational mechanics, for example, in the context of this access program, it's also on the individuals.
Okay, then thank you for the answers. And Professor Balzani will give you a short insight now in the topic modeling of fiber-reinforced membrane materials and presented you his task of the week. In the task, you can analyze two different structural problems, a simple air hole made of a textile membrane material and an idealized artery.
Yes, thank you, Mirko, for introduction. So basically, what the task this week will be about is modeling of fiber-reinforced membrane materials. So first I'd like to acknowledge Anna Zahn, a co-worker of mine who helped me with preparing these slides. She would also, in addition to me, be happy to answer any question that you may have during this week. So first I will give a short introduction or motivation. Then I will explain some continuum mechanical preliminaries that will be required for solving this task. And then I will basically come to the two main parts of this task. So first, which I call task 1, task 1 will be the calculation of a textile membrane of a lightweight structure, and the second task will be the calculation of an aorta under physiological blood pressure. Okay, with respect to the first task, we will focus on textile membranes. These are typically used in engineering applications as, for example, lightweight roof constructions, as exemplarily shown here, or also the roof construction of Dresden Main Station, and also facade cover design, weatherproof awnings, and so on. The main composition of the material is, as exemplarily shown here, that we have a rather isotropic, soft matrix material, and embedded therein we have a woven fiber network of rather stiff fibers. Those are the ones that are shown here. And they are rather wavy-like. In soft biological tissues, we have a conceptually similar material composition where we also have an isotropic ground substance and embedded fibers. Here, with respect to the passive response, typically the collagen fibers that are arranged crosswise helically around this arterial wall. So those two materials are going to be basically calculated in my task. So first, some continuum mechanical preliminaries that you may need. First, some assumptions. So we consider only idealizations as thin membranes, although we know that in particular diseased arteries may not be really thin. However, this is a necessary idealization to calculate this analytically. Then we focus on the small strain framework, although the materials undergo large strains, but that's just for simplification. And then we focus on a transversely isotropic model, which means that we have a stiff fiber direction A, and perpendicular to this we have isotropy. And we use this transversely isotropic for the representation of the individual fiber reinforcement. For these materials, we can calculate the stresses basically on the equation that is given here. So sigma would be the stresses in the small strain framework, and these can be calculated by a derivative of this strain energy function psi, which is a function of the strain tensor for small strains epsilon, with respect to these strains epsilon. Of course, this specific strain energy function has to be constructed for the particular material such that characteristic stress-strain curves that are measured experimentally can be matched. Here we focus on or let's say the particular strain energy function is given, so that's the specific form of the energy function that we consider here. It is decomposed into an isotropic part describing the matrix material and the superposition of two transversely isotropic parts that account for the individual fiber reinforcement. So that would be the transversely isotropic energy associated with one fiber, A. So A is the summation index from 1 till 2. Material parameters in here are first the Lamé constants here and this additional elasticity parameter alpha, which captures the elasticity in fiber direction. So basically the one responsible or associated with the collagen fibers. J1, J2 and J4 are so-called invariants, the basic invariants of epsilon given here, so trace epsilon and trace epsilon square, and the so-called mixed invariant, which is the trace of epsilon times m. M is the so-called structural tensor, whose coefficient matrix is 3 by 3 and the components ij are computed by the dyadic product of the preferred directions, the fiber direction A, so basically that's the index notation AI times AJ, wherein AI are basically the coefficients of the fiber orientation vector. So let's come to some remarks that are also required for the tasks. The material parameters, in fact the Lamé constants lambda and mu can be calculated in terms of the Young's modulus E and the Poisson ratio nu by these formula. So E and nu will be given in the task description that you find online. We consider in the task only rotation symmetric structures which are parameterized by polar coordinates. So R will be the coordinate in radial direction, phi in circumferential direction, and z in axial direction. Then we have neglected stresses and strains in radial direction, and the shear stresses are neglected and strains. So this simplifies the whole problem significantly, such that basically we end up with 2 out of the 9 non-trivial equations that arise from this derivative expression. So in index notation we have this formula where I is either phi or z. So we have basically 2 equations left, one for calculating the normal stress in circumferential direction, that would be sigma phi phi, or in an abbreviated notation where we skip the double indices would be sigma phi, which is then the derivative of psi with respect to epsilon phi. And for the axial direction we have the normal stress sigma z equal to d psi with respect to d epsilon z. Let us now come to the individual tasks. So the first task is the calculation of a textile membrane of a lightweight structure. The structure is given here at the left. So you see this roof construction, for example, for a swimming hall. And basically this shape is obtained by inserting an internal pressure which is slightly above the normal air pressure, and that keeps the structure in shape. So it's an air dome if you want. So based on this equation that we just saw, so this derivative which is equal to the stresses, we basically have a set of 2 equations with 4 unknowns. So the unknowns would be the normal stress in circumferential and in axial direction, and the strains in circumferential and axial direction. However, as we can see from the boundary conditions here, this is something like a plane strain state with normal in z direction. So basically we don't have any strains in the axial direction, which means that we can consider epsilon z to be equal to 0. The stress in circumferential direction, on the other hand, can be calculated from Barlow's formula, which is given here. So Pm would be the internal pressure, Rm would be the radius of this membrane, and Tm would be the thickness of the membrane. Here you see a sketch of a zoom, basically characterizing the main fiber directions. It's a woven fiber network, so we have the warp and fill direction. In this case, these directions are aligned with the polar coordinates. So what you should do here, once you know epsilon z and sigma phi, you can solve the system of equations for epsilon phi and sigma z, because these two equations only depend on two unknowns, and then you are asked to compare this with the ultimate values, epsilon phi max and sigma z max, to check if this construction would be basically okay or not. Maybe I should also mention in the full task description you find further small parts of the tasks and further details, so please take a careful look at those descriptions. Task 2 basically considers the calculation of an aorta under physiological blood pressure. So here you see a sketch of this idealized healthy artery. Certain parameters are also given in the detailed task description. What we notice is that first the internal pressure inside these human arteries is significantly higher compared to the internal pressure in the air dome that we considered one slide before. On the other hand, the fiber stiffness is relatively low compared to the textile membrane. So the question now is, how does this structure behave due to the internal pressure? Therefore, you are first asked to compute in the same way, basically, analogously to task 1, the values for epsilon phi and sigma z, and then focus on this task, which is, I would say, a rather toy task. Basically, although technically impossible, please check if you could, in principle, construct the roof construction in task 1 made of arterial tissue that is considered here. So that's basically what I want to say about the description of the task today. Thank you very much for your attention.
Thank you very much, Professor Balzani. Just that we give them the audience a bit of time to ask questions now. Can you just conclude in a few sentences the task of the week?
Well, basically it's based on a very simplified formulation, of course. I mean, normally if you would have would be interested in realistic calculations, you would require numerical calculations. So of course that's not something that we can discuss in this weekly task. Therefore I included some simplifications which enable the calculation of a textile membrane construction, which is this roof construction, for example for the swimming pool, and task 2 to compute the stresses and strains in this simplified artery.
Okay, I'm just looking forward to finding maybe some questions about misunderstood your task of the week, but just for notice, the task of the week, all the answers are handed in till Friday this week, not till Sunday, till Friday at 12 p.m. at midnight. Till then, the answers have to be handed in on the formula you find in our discussion forums, and therefore you need also the login, your username and your password to do so. And if you want to have a sheet that you did so, you need to hand in 5 of 18 tasks of the week. And there is a question for you, Professor Balzani. Why did you choose to go for this research field? It's a general question, not about the task of the week. Why did you choose to go for this research field? What personal interests you about that?
That's a very good question. It didn't really come by perfect decision, I would say. It was not like I was sitting in my office and thinking, oh, what should I do? And then I decided, okay, that sounds great. It was more like I was working on so-called polyconvex strain energy functions, and soft biological tissues were a very reasonable application of these mathematical formulations. Lots of challenges in these soft tissues, like anisotropy, incompressibility, large strains, and as I said, these living tissue matters like growth, remodeling. So for me, it's really, I mean, as a mechanics or a person working in mechanics, this is really fantastic, this material. I mean, to describe this and to model this and simulate this. Also very interesting for me is the interdisciplinary character of this. So we've been working a lot with experimentalists, with mathematicians, and of course with medical doctors. I mean, that's a strong collaboration here with respect to several things like experimental data, patient-specific geometric information, which is typically obtained by, in our case, from intravascular ultrasound, such that we can really make a very complex three-dimensional geometry of the artery, including all the individual tissues that are in there. I mean, this is what I just showed, really a simplified geometry. The artery consists of several layers. If there is an arteriosclerotic plaque, the plaque is even decomposed into fatty tissue, fibrotic tissue, calcifications, lipid pools, so really complex geometric structures. That's probably why I chose this biomechanics field, I would say. The other focus on micro-heterogeneous materials in general is basically, I think there's so many things yet to be discovered with respect to new materials. So it's also a very interdisciplinary field where you can talk to a lot of scientists that are in material science, or even really working on the developing of new materials or on the production of new materials. Lots of issues where computation simulation is important. So that's what I like, I would say, about these things, the interdisciplinary character, and of course the challenges that are posed by these complex materials.
As you said about the interdisciplinary character in your research field, are there any cooperations with other TU9 universities? You know about
TU9 university, I never really thought about this so particularly, I have to admit. So now I'm not sure.
Do you know about any other cooperations with other universities about this research field?
Well, basically we have a lot of collaborations going on. I mean, basically a group with mathematicians in Cologne around Professor Clavon. Then I've been collaborating on these textile membranes with Professor Gruppmann from Darmstadt. Then there's Oliver Reinbach from Freiburg, also with respect to these multi-phase steels and arteries. I mean, I could really endlessly go on with listing up other cooperative partners. Also in the US, I mean,
there are a lot of collaborations between other universities all over the world,
exactly.
As you said. Okay. And then the last question about answering questions to the task of the week. Who is answering the questions during the week in the forum?
Basically, that's going to be Anna Zahn, a co-worker of mine, who is also working on or started to work on these biomechanical tissues. But I will be also open. I mean, it's not like I am out of business then. So I would be happy to help in any sense, of course.
Okay, then thank you very much, Professor Balzani. Thank you very much to Dresden, and thank you for your answers.
Thank you very much too, and have a lot of fun doing the task, of course.
Thank you, and bye-bye to Dresden.
Bye-bye.
And now we are going to have a deeper insight into our second topic of the week, and this is, can we hear the sickness of ice? Therefore, we switch to Munich to Professor Müller. And before we start, let's get a short portrait film of him and the TU Munich.
Grüß Gott and a warm welcome. My name is Gerhard Müller. I am the head of the Chair of Structural Mechanics here at the Technische Universität München in Munich, Germany.
In our institute, we deal with vibroacoustic problems, ranging from structures in civil engineering to components of the automotive industry.
In order to tackle those problems, we need strong models. The models have to be designed such that they are able to describe the relevant phenomena, typically using mathematical equations.
The Lamé equation, for example, permits to describe the wave propagation in the soil caused by a train passage. Here you can see how the soil is shaking.
Of course, our models are not able to describe the world as a whole. The reality is reduced by them to the important aspects of the problems we are dealing with. This can be, for example, the model of a bridge that is loaded by pedestrians.
We create the model, predict the vibration and check the results to ensure that the students cannot destroy the bridge by jumping and shaking. As we have measurements of the real structure, we can even compare them now with the results obtained with our model in order to calibrate it.
In contrast to real structures, investigations can also be carried out at model structures in our laboratories.
Look, our colleagues are playing. No, they don't play. They are doing research. They check in how far the models they developed fit to the measurement results at the model train, with which the typical train-induced dynamic forces, ranging from the regular passing of the sleepers to the roughness of the wheel or the irregularities in the track, can be assessed.
We, the engineers, are able to predict important parts of real life with clever mathematical models in order to optimize our structures and to predict the responses of our systems. Feel invited to join our programs at the Technische Universität München.
Now I would switch to Munich, but because of the fact that Professor Müller is the Senior Vice President of Academic and Student Affairs since the 1st of October 2014, today he needs to notice a shortly scheduled meeting. And therefore we recorded the interview last week, but you have also the choice you have the chance to ask questions to him, maybe not to him in person, but to the head of chair of structural mechanics, to whom we switch after the interview to Mr. Dr. Buchschmidt. But before, the interview with Professor Müller. Now I'm looking forward to talking to Professor Müller, who conducts research into structural dynamics and vibroacoustics in Munich. Welcome in Munich, Professor Müller.
Hello, everybody. A warm welcome to the students and to all the persons interested in this format.
So my first question to you, Professor Müller, is why do I have to study a master program for civil at the Civil Geo and Environmental Engineering Group at the TU Munich?
Well, nobody has to study a master program at our university, but we strongly recommend it to everybody who comes with a bachelor's education from various fields of engineering. Typically, the students arriving in the bachelor's programs, they have not yet perfectly identified their talents and their interests. After the bachelor's, for example, a bachelor in civil engineering or in environmental engineering or also in geodesy, they are able to identify what they are interested in, where they might have a good performance, and where they also see some perspective for their future professional life. And then they can choose among various master's programs, which might be a little more general, like the masters in civil engineering or in environmental engineering, or which address specific issues also linking to other disciplines, like, for example, a master's program in computational mechanics, or a master program, one of the master's programs in the field of transportation. So what we think is that after the bachelor's, you have the possibility to already focus on the visions you have for your future professional life. And therefore, I think one should recommend to everybody who passed successfully a bachelor's program to think about an appropriate master's program in the following process. There is another reason. I think students, when they have finished their bachelor's programs, are typically very young. And it would be a pity if they wouldn't invest their lifetime, their valuable lifetime, for further studying and learning. Also taking into account that in this period of life, in the first half of the age between, or that in this period of life between 20 or 28 years old, you are very good in learning additional things and you will profit from them for the rest of your professional life and also for your way of thinking about processes and systems.
Yeah, so that are the general information about studying after a bachelor, studying a master program. What especially are your offers for international students? What are you offer them to come to Munich?
Yeah, so we offer for our international students a whole series of tailored master's programs addressing various topics, but also our master's program in environmental engineering is 100% in English language. So we offer different options to the students, and we try to focus on various issues. It can be either an issue where we say the competencies in our faculty in research can be bundled in a way that we provide students knowledge for also penetrating into different fields afterwards. It can be the automotive industry, but also the industry in civil engineering. This is the masters in computational mechanics as an example. We also have master's programs where we try to bundle specific competencies for transferring the knowledge that has been developed in our research and also in our administration for the world. This is, for example, the case in the master's program, land management and land tenure. So to summarize it, we try to offer to our best international master's programs in order to attract interested, talented people to TUM, and they can right from the start in those master's programs start to study in the English language. However, we recommend to everybody to acquire during his stay here in Munich sufficient language in the German, However, we recommend to everybody to acquire during his stay in Munich a sufficient knowledge of the German language in order to also be able to choose freely where to work after the master's program.
And can you give us a number? How many % are international students?
Well, we have in the master's programs approximately a number of 30% of international students. This depends on the program. We have several master's programs where we almost have just international students with very few German speaking students, and but the typical number of all the courses is approximately 30%.
So what distinguishes, if we have a look at the graduates, what distinguishes the graduates of the master program Civil Engineering and Computational Mechanics at your university?
Well, we try to provide to all the students the knowledge to handle the key elements of the engineering disciplines in the respective fields. So our focus is to provide them with profound competencies in the modeling aspects of our engineering disciplines. What does that mean? Our students, after finishing the master's programs, they will have the task to solve different types of problems where different elements from various fields of science penetrate. This might be the natural sciences like physics or chemistry. It can also be strong parts of the social sciences. Just think about building a new system for transportation, a new tunnel in some city where we have to communicate also to politicians, and it's also a large amount of processes, of the dealing with processes and uncertainties. All this together has to be combined also with the assessment of the impact of human actions on the environment, and we aim that our students are able to bring the different fields together, to have the competencies to handle these multidisciplinary problems.
And if we have a look at the everyday student life, how do you implement these aims into the teaching?
Well, implementing this aim into teaching is, of course, manifold. One element is that we clearly try to find out which parts, which knowledge, which skills are necessary in order to acquire the competencies I just mentioned. So acquiring knowledge is, of course, a course where you teach the contents to the students, for example, in the format of a lecture, focusing on the crucial elements. Then you have to train these elements in acquiring skills. So skills is then might be a project work with several students. It might be a talk presented by the students, but it can also be complicated calculation at the basis of a model. So we try to identify then whether those skills are mature enough in order probably to provide some additional knowledge. And after this circle, providing knowledge, creating skills, finally we are very confident that competencies arise.
And if that is the theoretical part, how much do you work with your students in practical stuffs?
I think when discussing practical issues, you have to be very careful. There is a clear reserve, frankly speaking, to practical issues, which can be much, much better taught and trained on the job in the first months or probably in the first year on the job. This is, for example, the handling of a computer code. So, of course, our students have to know what is behind a program with which you can calculate complicated structures. They have to know about the theory, but they have to be aware that once they come into practice, one company works with one code and the other company works with another code, and it is not really and it doesn't really make sense to teach a specific element. So the practical aspect is to know the background, to have skills in applying the systems exemplarily, but not to be trained in a way to work like a professional who does the job since several years. The same holds for standards. It is very important that the students know in engineering that standards exist, and they also know the key elements, how a standard is elaborated, how a standard is influenced, by what elements a standard is influenced, and also what theory is behind. But of course, they will not leave the master's course as well-trained persons who apply these standards like a professional after several years again. This would be a waste of time, and we've tried to focus in our programs very much on the contents, which are very, very difficult to acquire later on in a professional surrounding, just due to the time and also the concentration they require. However, of course, in the master's programs, practically all the contents we are teaching are visibly, clearly linked with practical issues. For example, the simulation of a complicated flow in fluid dynamics, of course, people are aware of the practical questions that are behind, for example, in the river flow management or in the design of water power plants. So this is clear that the practical link is always there. In addition to that, of course, we make excursions to practical projects. And what we also encourage, of course, is that in students' project works, we have links to people coming from practice, that they listen to the presentations and probably also support it. Several master's theses are done in companies, are prepared in companies in order to have this practical link. So there is a manifold scheme for practical links. However, one shouldn't replace the training on the job in companies by the university education, or the university education should not suffer from some basic needs which can be much more elegantly and in a smoother way acquired in a company.
Can you give us here as well a percentage, a number, how much, how many percent practical, or is a practical part in the master program, or and the theoretical?
I would frankly say that in the master's program, 100% has a clear link to practical questions. So the students are aware of the practical questions. However, it might happen that they calculate at some idealized structure, which at the first glance, for a person who is not an expert, but the students are already experts coming from the bachelor, doesn't show an obvious link to some practical applications. But if you take, let's say, a wind simulation, a flow simulation of an airflow, or the simulation of an acoustic field for a non-expert, for a person who has no idea about acoustics and flows, it might look completely theoretical. However, for a student coming from a bachelor's program with an engineering content, he clearly sees, okay, there is a link to this or that practical issue. So I would say everything has practical links. However, for many issues of practice, you need a thorough understanding of theory. Yeah.
Thank you very much for the answer. And if we have a look at the nearer future, if the graduates are jumping on the job market, what chances do they have if they graduate at the TU Munich?
Currently, they have excellent job markets. There is a strong need for talented engineers in Germany, and therefore one can say that our graduates really can decide where to start the first professional activities. On a long run, I think one should not just address the job market, which I'm very convinced will be positive also in the future, but also should focus on the key challenges they have in applying their knowledge for shaping the future of the world. And there I would say that our graduates in the engineering disciplines we teach have an enormous variety of possible work and possible challenges to handle. You know that in many countries the systems which are provided by civil engineers are not yet developed in a way that they protect the environment sufficiently, or that they provide an adequate way to live for the people. Just think about the questions related with the supply of water. So our engineers are facing worldwide challenges in the less developed countries just to implement the systems we are already available to implement. And on the developed countries, there will be an enormous change, and I'm convinced about that, in the fields of many aspects. Aspect of energy saving, resource efficient building and systems, also the aspects of the behavior of younger people towards mobility and the challenges arising from that, just to mention two of them. So there will be a good situation on the job market, but even more important, to my opinion, there will be an excellent field of bringing in one's personal creativity for shaping the world.
Do you think that there are, if we look worldwide, they have chances on the job market? And you told us something about the challenges. Do you think that there are any social challenges when that you heard of?
Social challenges, of course, political challenges and social challenges. This is an enormous field for our graduates. Also, again, in the developed countries, to implement new systems in the societies, in democratic societies. Just think about the processes we are discussing about the large infrastructure systems like the station, the railway station in Stuttgart, or huge airports, or the transport of energy from northern Germany to southern Germany. This is an enormous challenge where the people from the civil engineering and environmental engineering faculties have to play a key role in informing the population about the implications. And there is another challenge, of course. People studying, for example, the program Land Management, Land Tenure, which I just mentioned before, coming back into their home countries and implementing new systems of land management there and discussing the advantages in their societies. So our graduates have to have a thorough knowledge how to deal with societal processes, and this makes the professions our students have even more interesting, of course.
Okay, thank you very much for the detailed information. Therefore, I want to ask you my last question, and we want to try to create a German engineer of the TU9 network, and therefore I want to ask you what special skill do you think has a graduate from the TU Munich if we personate a German engineer? What do you think if a graduate of TU Munich, what is important? What do you think?
Well, the German engineering, I think, has to get more and more in the situation that it is able to merge the different disciplines coming from all the fields of science which are related to the systems we create. This is, I think, important that we here in Germany are aware of this, of changing also our curricula in this direction. So what does that mean? We as German engineers, we are linked with natural sciences, with mathematics, with social sciences, with economy, with political sciences, also a lot with psychology of the people using our systems, etc. And we have to bring, and this is to my opinion the core of engineering, the elements of all the different fields of sciences that are relevant for our systems, for our products, for our ideas, together, to merge them and to create an optimum out of this. And this requires an enormous amount of interdisciplinary thinking, but it also requires the consciousness that creating systems is not just the work of a single person or a single discipline, but it is the result of bringing various persons, various talents together. This, I think, should be a key issue for German engineering. By the way, German engineering in general, and this is beyond TU9, consists also of different formats of engineering provided by different educational institutions, by the universities of applied sciences and the scientific universities we are representing at TU9. And therefore, I would say that we also should be aware of the fact that also in the future it is good to provide different components of the systems for different talents and different interests. And therefore, I think, in total, we should maintain a lot of elements of our systems, but we should more and more be aware of the connection of the different disciplines in an interdisciplinary way.
So, and therefore, thank you very much for the interview, and thank you very much to Munich, to Professor Müller for answering my questions. Thank you very much.
Thank you very much, and for everybody, a nice continuation of this MOOC process.
Yeah, and thank you, therefore, for those who connect to us lately during the interview with Professor Müller. We recorded it last week because he's today important meeting, a short scheduled meeting. But before we come to our question-answer part, we switch to the task of the week. And as I said, the topic of Professor Müller is, can you hear the thickness of ice? In his task of the week, you have to determine several variables of this thickness of ice, and after that, you have to decide, based on your calculations, if you would jump on it. Here it is.
Welcome, dear students, to our sessions on models in civil engineering from cardiology to fishery. In our today's session, we will deal about the aspect of fishery, regarding the issue, the observation that in Arctic regions, fishermen can hear the thickness of ice when ice cracks, or in the case that somebody jumps on the ice in their vicinity. So why can they hear the thickness of the ice? In order to understand this, we should model the whole problem into its different components. So on one hand side, we have an acoustic fluid where sound is propagating and which transports energy to the ears of the fisherman. Why is energy transported to the ear of the fisherman? Because energy is propagating in the ice, which we will model as a plate in bending, excited by some jumping person, which induces impulses into the structure. So our today's task is to split this problem into its different components. First of all, we will talk about the plates in bending, which will remind you of the things you have learned about beams in technical mechanics in your previous studies. Secondly, we will then focus on the wave propagation in such beam-like structures or in plates, which is very similar. Thirdly, then we will deal with the issues of wave propagation in acoustic fluids, where the sound energy is transported to the ears of the fisherman. Point 4, we will try to understand how the sound radiation in the air takes place. In order to understand all these elements, we also have to focus on the issues of Fourier analysis and spectral analysis, which I will address very briefly in the presentation. So let's start with the plate in bending. You see here a plate which is described by a coordinate system x and y. Perpendicular to the plate we have the coordinate z. The plate has some thickness which is given by the value t. It has a Young's modulus E and a Poisson ratio nu. Out of these values, in the scope of the Kirchhoff plate theory, a bending stiffness which is given by this formula can be derived. Furthermore, the plate has a mass, and the mass is described by the value mu, which is nothing else but the density times the thickness of the plate. So it has a dimension of something like kilogram per square meter. The plate then is described by the so-called Kirchhoff model, which I will not address in detail. You probably have heard about that in your courses of technical mechanics. So this differential equation, a partial differential equation of order 4, has different elements. It has partial derivatives of the displacement of the plate in the perpendicular direction w with respect to the x and to the y coordinate, and it also has a partial derivative with respect to the time, where the inertia effects of the plates are represented. On the right hand side you have some load which is exciting the plate in the z direction, p of x and y and t. So in order to solve this differential equation elegantly, we make an approach which is, for the experts among you, based on a Fourier transformation. For those who are not familiar with that, they just should assume that all the solutions and the excitations are described by a superposition of sine and cosine functions with respect to x, to y, and to the time t. For those who are familiar with complex values, they know that such functions can be nicely described by this Euler formula, or you can also describe them in such a way. We, however, in the following will stick to this type of representation. Taking this harmonic approach and putting it in the partial differential equation, we obtain a simple algebraic equation which links the load with the displacement by such a formula. The elements of the solution can be visualized by propagating waves in the plate, and if we take a beam in the one dimension of a beam. These waves have a certain wavelength which is given here, and this wavelength is called lambda. If we describe the function with respect to time, this lambda corresponds to the period of vibration, which typically is described by capital T, and can be calculated out of 2 pi over omega. You also see that out of a superposition of these oscillating functions, we can construct a standing wave, like you see here with the black line, which we observe in delimited plates. However, we now consider an infinite plate, we consider the ice, which is excited by the jumping person. So, if we now take the ice without an external load, we can skip the right-hand side of the differential equation, where originally we had the load, and we place a 0 on the right-hand side. Such an approach now leads to the ratio of the wave numbers kx and ky and the angular frequency of oscillation omega, which you see here. One can show, and I don't show it here explicitly because it would take too much time, but you can try to understand this on your own, that the combination of the wave numbers kx and ky can be interpreted as a wave number kb, which is somehow inclined with respect to the x and the y coordinates of the plate. And we thus obtain now a ratio between this wave number kb and the angular frequency omega, which is given by the quotient of the mass per surface area and the bending stiffness of the plate. Putting those things together and knowing about the relation between the wave velocity of the propagating waves, like we have in the two directions, the wave length and the frequency of oscillation, we finally obtain a nice relationship between the bending wave velocity, the angular frequency, the bending stiffness, and the mass per surface of the plate, which will be decisive for the understanding of the phenomena we are dealing with. If we draw now this bending wave velocity with respect to the angular frequency, you will see that we have here a function which depends on the frequency. We call this phenomenon as dispersion of the bending wave, and we also can draw a function of the bending wavelength with respect to the frequency, which you see here on the right-hand side of this picture. Now, taking some load which is exciting a plate, we then can see here different patterns depending on the frequency of excitation, and you see here for higher frequencies we have shorter wavelengths like on the right hand side, and for lower frequencies we have larger wavelengths as results for our harmonic single load exciting such a plate. Now we have described the plate satisfactorily, and now we go on to the acoustic fluid in order to understand what happens in the acoustic fluid once a plate at the delimiter xy at some plane of this acoustic fluid is exciting the fluid. So again, we take in the first step the partial differential equation which can be derived for the acoustic fluid. You have here in this partial differential equation on one hand side the acoustic pressure describing the acoustic situation in the fluid, and on the other hand side you also have here the wave velocity, the speed of sound in the acoustic fluid, which we call C sub A. This differential equation now can be solved with a similar approach where we again describe the pressure with respect to the x coordinate, the y coordinate and the time by harmonic approaches with the wave number kx, ky and the angular frequency omega. So what remains is now one element which is described by EI kz, and the question now is, what is the character of this element? And this character will be decisive for our problem, I can promise you already now. Now, what can we do? We now place this approach in the differential equation, and you will see that the first element, the second element and the last element, the fourth element, will simplify considerably, and also the third element will simplify by this multiplicator with the value kz, and we have a simple equation with which we can calculate this value kz, describing the behavior of the solution in the z direction. So the question now is, what is this behavior like? So our new approach is given in this form, and you see here we have in the z direction a certain element which we will discuss now a little more in detail. We abbreviate this element now by substituting this element by Ka, the wave number in the air. Now, taking these forms, we now realize that the solution in the z direction depends considerably on this value Ka compared to the values kx square and ky square. In the following way: in the case 1, when Ka square is larger than kx square plus ky square, we obtain in the z direction a solution which again is harmonic. That means that we have in the z direction also a sinus and cosinusoidal dependency of the pressure with respect to z. One can now show that this solution is linked with a wave which is propagating under a certain inclination from the plate into the fluid, and this wave can be described by cosine and sine function with respect to z. In the second case, when Ka square is smaller than kx square plus ky square, the exponent of the exponential function becomes real. And as you know, a negative real exponent is linked with a decaying function, which you see here. That means that the pressure decays from the xy plane, and if the person, the fisherman standing here, has such a size, he will probably not hear the sound field anymore, whereas if he's standing here in this wave pattern, he will be fully affected by the sound field which is propagating from the plate. The first case we call propagating waves or far fields. The second case we call evanescent fields or near fields of this radiation problem. That means that just under certain circumstances, namely in case that the bending wave length, which is given here, lambda b, is larger than the wavelength in the air, which I call here lambda a, we have this radiation phenomena. In the other case, if the bending wave length gets smaller, shorter than the wavelength in the air, we will have evanescent fields which just cause near fields which radiate very poorly. In the limit case, when both wavelengths are equal, or in other words, when the dispersive bending wave velocity is equal to the non-dispersive speed of sound in the air, we have the so-called critical frequency, and this critical frequency is then decisive to decide whether the problem radiates or whether it radiates not really. So let's couple now the air with the plate, and you see that the speed of sound in the plate Cb and the speed of sound in the air Ca will cross at a certain critical frequency at this limit case. Above this critical frequency, the bending wavelength is longer than the wavelength in the air, and we have a radiation of sound. Below we have these evanescent fields. And depending on the thickness of the plate, you see here different crossing points, different critical frequencies, and this means that at the basis of the critical frequency you can deduce the thickness of the plate. Now we have described the plate, we have described the fluid, and now we should focus a little on the load. And as you probably know from your courses, we can look at an impulse load and describe the frequency content of an impulse load by taking the impulse load, assuming that this impulse load repeats after a certain while t, and then carrying out a frequency analysis, which is also called Fourier analysis. We make a Fourier series for this load. The Fourier series is given here, so you can cross-check it on your own if you are interested in. And if we have one single event, we can increase this t towards infinity, and we come from the Fourier series to a Fourier integral to the Fourier transformation. which shows that the load P of t, which is a very short impulsive load, can also be described in the frequency content by a P of omega with constant values independent of the frequency, so constant over the frequency range. So this means that by this impulse, or also by the crack, we will have a very broadband excitation from high to low frequencies. So now let's conclude. Our excitation contains, in an ideal case, all frequencies. Just above a certain frequency, F larger than F critical, sound is radiated and can be heard by the fisherman. The high frequencies are linked with a higher bending wave velocity, and they can be perceived earlier at the different locations. The lowest frequency, which is linked with a strong radiation of sound, is the critical frequency. The critical frequency depends on the thickness of the ice layer. So, of course, if we can detect the critical frequency, if we can hear the critical frequency and describe it, we can deduce from it the thickness of the ice. Let's go to an example. So here you have two different thicknesses of the ice, and in the first case, which is shown here, the ice would sound like that, starting at high frequencies and finishing at a certain critical frequency, where the speed of the bending wave is equal to the speed of sound. In the second case, the other type of ice will have its critical frequency here, and then you will hear a kind of different sound. Let's hear the first sound. Let's hear the second sound. So now we come to the task, and we would like to think about the following problem. So we have two different types of ice, a layer 1 and a layer 2. Let's listen to layer 1. Let's listen to layer 2. Unless you have an absolute hearing, you will not be able to tell us what is the frequency the signal finished in its process. So let's measure it. So we measure the first layer and we measure the second layer. You see here on the left-hand side the description of the sound pressure versus time, and frankly speaking, you see nothing. So in order to analyze those signals, you should make a Fourier transformation, which is done here, and represent the signals in the frequency domain. And you see here that the red signal, the upper signal, has a frequency content which finishes approximately here around 250 Hertz. Whereas the green signal has a frequency content which finishes approximately here around 1500 Hertz. So you know now the frequency limit of the perceived sound. On the other hand side now, you also have some assumptions concerning the Young's modulus, which is given here, the density, which is given here, the wave velocity, the speed of sound in the air, and the Poisson ratio. So with these values, you should now be able to assess the thickness of the ice, knowing the lower frequency of the perceived sound. The question now is whether this model you applied here is conservative or not. You should for this assume in the whole process of our derivation which elements we neglected. There was one important element which we didn't take into account. You should think about that. Which element was that? And then I would also like to draw your attention to the results that have been published by Lundmark in the year 2001, who correlated the thickness of ice with the perception of fishermen who had the ability of absolute frequency perception. For the experts among you, for those who know the differential equation of the Kirchhoff plate and also know the relevance of the different elements, I would like to ask you to estimate the stiffness of the water using the model of an elastically supported plate. comparing your results with the results obtained by Lundmark. You then can get a feeling of the limits of your model, and you can also get a feeling of how models can be calibrated by measurement results. I hope you have enjoyed this short course. We wish you valuable insights in solving the task, good solutions. We are looking forward to see your solutions, and we finally wish you a nice rest of the day.
Therefore, first of all, thank you to Professor Müller, who is not in person in the MOOC at TU9. And now I'm looking forward to switching to Munich and to the head of chair of structural mechanics. Welcome to Dr. Buchschmidt.
Hello, Mr. Spohn.
How are you doing today?
Fine, thank you. And a warm welcome to all the participants of our course.
There are some questions, and now we have the question and answer part. Therefore, I hope you can give us the answers, Dr. Buchschmidt. First of all, what are all the prerequisite skills that are expected from the incoming students for Masters in Computational Mechanics program at the TU Munich?
Okay. Computational mechanics is one of our international programs. Therefore, the field of applicants is in general all over the world. And the prerequisites are you should have an above average graduate, or you should be an above average graduate of one of the following disciplines. Could be civil engineering, could be mechanical engineering, or automotive engineering, or something similar. In general, it will be done, then checked whether you fulfill the prerequisites, also concerning your background in mechanics, mathematics, and computer sciences. But feel free to apply also if you are out of the field of aerospace engineering, or in general if your background is linked to mathematics, engineering, and if you like to do modeling and describe problems with differential equations. If you are a foreign student, in addition to that, and if you're not an English native speaker, you would have to fulfill, or you would have to prove your English skills, for example, with the help of a TOEFL test or something similar. So this is in general everything concerning the prerequisites.
Thank you, Dr. Buchschmidt. Another question is, could you please explain again the difference between dispersive and non-dispersive wave propagation?
Oh, thank you for this interesting question. There is a big difference. The main difference is that the propagation velocity in non-dispersive media does not depend on the frequency. In acoustics, for example, the velocity of wave propagation is always around about 340 meters per second for all the frequencies, which is very important, for example, if you would like to communicate via the medium, via the acoustic fluid. If this would be not the case, which means if the propagation of the sound would be frequency dependent, then the signals I would send to you would not reach you in the same amount of time, which means the higher frequent parts would reach you earlier than the lower frequent parts, and therefore the whole signal would be destroyed, which means for communication in acoustics it is very important that this is a non-dispersive medium. For wave propagation in beams or plates, for example, it's another effect that the wave propagation velocity for the banding waves depends on the frequency, which means the higher frequent parts, they propagate faster than the parts with the lower frequencies. And that is also the reason why if we couple the acoustic fluid to the vibrating blade, which was done in our MOOC, we get a frequency where both wavelengths then coincide, and then at a higher frequency than this frequency, which is called the critical frequency, the radiation of sound works, because then the radiating plate has got a longer wavelength than the acoustic fluid, and therefore for the sound radiation an angle of incidence is found where this radiation is possible.
Thank you. And I have another question, maybe a little bit off topic, maybe a little bit ethics or philosophical. What is the responsibility that each engineer carries each moment while and after modeling structures in reality and implanting into reality?
This is a very difficult question, and it's a question I think every engineer and every everybody within the group of our graduates has to deal with, sometimes the whole life. Of course, you are responsible for the structures you compute, you model, and you design, as all the engineers in civil engineering and automotive engineering, because our customers and the people living with us, they trust in us and they have to trust in our models. Therefore, the responsibility is quite a high one, and I just can recommend you to be based on a good theory, which means deal with the basics, try to get enough knowledge in mechanics, in mathematics, so that you have a good, strong mechanical and theoretical background, because then you have the best chance to identify problems and traps in reality, in real life, in modeling, and therefore then you have a good chance, or you can trust on your own and on your models, so that you can sleep quite good during the night.
Okay, that sounds good to me. So the last question also to you, what focus do you have in your curriculum?
From our point of view, concerning the chair of structural mechanics, we focus on the basics in mechanics, which means one of our most important subjects is called continuum mechanics and tensor analysis, where we deal with the basics, with the mathematical basics in mechanics, with the different equilibrium formulations, and then we go into the field of applications, which is in our case, for our chair, it is vibroacoustics, which means structural dynamics and acoustics. In addition to that, we complete the program with lectures where we enrich the background in integral transform methods, very mathematical. We have lectures concerning measurements, vibroacoustic labs, for example, where students can deal with measurements and measurement equipment. We have additional lectures concerning stability of structures, for example, but also soil dynamics. So everything which is linked with vibrations, with acoustics, and with mechanics.
Okay, then thank you very much for the answers to Dr. Buschmidt. Thank you very much to Munich. Have a good day and a successful week.
Thank you.
Now we come to the end of our second live session of the MOOC at TU9. Just some short information about structural technical stuff. You will find the download link for the tasks of the week in our discussion forum. You have till Friday, the 31st of October, you have time to hand in the answers, and therefore there's a formula, a submission formula where you can hand the answers in. After or on Sunday, then there will be a week conclusion of all what happened this week in the second live session week of the MOOC at TU9. And if you haven't had the chance to watch the whole live session, the 90 minutes, then in a few hours you will find the live session, the second live session on YouTube. Next week, our topic is digital engineering, and therefore from advanced physical layer technologies in 5G to secure services. And next time on Monday at 2 p.m. And our two topics are massive MIMO, and the second one is security engineering, building reliable IT systems for the world of tomorrow. I hope you enjoyed the second live session at the MOOC at TU9, and you will just try it out. Just hand in your correct answers, or your answers, what you think is correct, and be a part of it. Be a part of the MOOC at TU9. That's it for today. I wish you a wonderful day, a sunny week, and a successful week. And see you next Monday at 2 p.m. Goodbye, bye-bye, have fun.